Hi, everyone. This is the Hungry Math Professor here, and thank you for coming to my channel. And today I'm going to be talking about this paper entitled Computing Machinery and Intelligence that was written by Alan Turing. It was published in the journal Mind, which is like a philosophy journal typically, in 1950. Uh, and this paper is famous because it's the paper in which Alan Turing introduces what we now call the Turing Test. And of course, he didn't call it the Turing Test because you don't name something after yourself. You let somebody else name it after you. But he calls it the Imitation Game, which is the title of this movie about Alan Turing that you may have seen, and how he broke some codes using a machine that he made. And Alan Turing lived from 1912 to 1954, so this paper was published 4 years before he died. And I think a lot of us know the Turing test in some way, shape, or form. Very famous, or it was in the movie Ex Machina that came out in 2014, which is a very good sci-fi movie. There, they talk about the Turing test quite a bit. And it's usually presented in the following way, at least is the way I've always heard it presented, which is that a human is interacting with a computer, but in such a way it doesn't know who it's interacting with. So it's like chatting with something. It could be a person, like via text, or it could be a computer, and it's chatting via text. And um, the point of the game is if the computer can convince the human that the human's talking to another human, then the computer has passed the Turing test. It means that its behavior is human enough alike to where it can convince another human that it is human, right? And this is what happens in Ex Machina. The um, the AI system robot is able to sort of befriend a human and get them to help the machine get out of this prison that it's in. And anyway, it's a very good movie. I won't ruin the rest of the movie. Maybe I already ruined it for you, but if you haven't seen it, it was 2014, so you have plenty of time. What's interesting though, when you read Alan Turing's actual paper here, is you get a slightly different version of the Turing test of the imitation game, as he calls it. And it's actually a little bit surprising for the modern reader, I think, because the way he first sets it up is he says, imagine you have a man, a woman, and an interrogator. So you have three people. And the interrogator is going to communicate again via text with this man and this woman. And the goal of the interrogator is to determine who's the man and who's the woman via just like questions over text. And neither the man nor the woman um, has to answer the questions accurately. They can answer it however they like. Now, this seems like a weird setup, right? I mean, first of all, it doesn't feel to me like just via text I can tell somebody's gender, especially if they're trying to deceive me. I just don't think that that's the kind of thing you can determine via text, or at least I'm not so sure. It's kind of like an interesting side question. It's certainly not what we're trying to get after here. And it does seem like a distracting way to bring up this test, actually. But Turing I think he seems to think that this grounds the question a little bit for us. And in any case, after setting it up like this, where there's an actual man and a woman, both humans, talking to an interrogator who's also human, and the interrogator's job is to determine who the man is and who the woman is. He then says, okay, well, let's say we swap out the woman for a machine and now have the interrogator do the same thing. Somehow, maybe this is supposed to be some kind of control in the experiment. I don't know. I think it's a little bit bizarre. But in any case, that's how he sets it up. And again, I've never heard the Turing test set up this way because I don't think it's absolutely necessary to set it up that way. But it is interesting just to note that that is how Turing does set it up. But again, once he says, trade out the woman for the machine, now the goal of the interrogator is to determine who the machine is and who the human is, right? And that's the question. And Turing is setting this up as a test for determining whether machines can think. Because in the very opening to the article, Alan Turing poses the question, the very simple question, can machines think? Simple in the sense that I can state it very simply, but not simple to try to address it. And later on in the paper, it turns out Alan Turing is very clear that he just finds this question to be too vague, too open-ended, not clear enough, and he thinks it's kind of the wrong question in that phrasing. And so he's arguing in this paper that what we need is some kind of like concrete test that we can perform, and that's what he provides for us. And this is a form of what we call behaviorism, or saying that what it means to be thinking is a function of your behavior that we can just sort of observe, right? And if you're able to behave in such a way that you can convince somebody else that you are um, thinking or you are human, then that is what all it means to be thinking or human, right? And this is something that Ned Block, in his famous paper, um, Psychologism and Behaviorism, argues that this is not enough, that behaviorism is not quite the right approach. But anyway, we're not going to get there today. I'll talk about that famous paper where that includes the blockhead experiment in another video, but I just wanted to bring it up. But Alan Turing is representing this behaviorist view here and arguing that all we have to do to study whether machines think is to analyze their behavior and test their behavior in some way, and he provides such a test. Um, and you know, again, at one point in the paper, he says, I should give you my view here, and so he says, it will simplify matters for the reader if I explain first my own beliefs in the matter. Consider first the more accurate form of the question, meaning, I believe that in about 50 years' time, it will be possible to program computers with the storage capacity of about 10 to the 9 to make them play the imitation game so well that an average interrogator will not have more than 70% chance of making the right identification after 5 minutes of questioning. The original question, can machines think, I believe to be too meaningless to deserve discussion. So he makes a bold prediction here. He says, first of all, he says, can machines think is, I believe, to be too meaningless to deserve discussion. I think that's a little, I think he does go a little too far in oversimplifying that, what that means. But anyway, he makes a very bold claim and says that's too meaningless. And instead, I'm going to pose something very well defined. At least he argues it's very well defined. And he makes a bold prediction that, in about 50 years, we will have no more than a 70% chance of making the right identification after 5 minutes of questioning. Now, 50 years puts us at around 2000. So I think he was definitely wrong in his time, but who cares? I'm not trying to hold him to the time frame so much. Let's give him till 2025 or whatever in the future. We can only go so far as 2025 right now. Um, I don't know. So part of the problem I think with the Turing test is it's not clear like who qualifies as the right interrogator in this imitation games experiment, right? So much of the experiment hinges on the actual thinking of the interrogator themselves, right? It's possible that that maybe, no more than 70% of humans alive right now would get it correct. But is that the right test? Like, are like a lot of these people simple-minded in some way and they're not very good at determining this? They're not the kinds of people who've had a sophisticated thought about what it means for computers to be intelligent or not, and so they're not very good interrogators. Um, there's no real description of, you know, you kind of want some like minimum bar that an interrogator has to meet in order for them to be like the right interrogator or something. Now, I think this probably is something Turing avoids because it would open up a whole nother can of worms, and but I think it's an important thought to have here, like what qualifies as a good interrogator. And just because someone is convinced, like, I mean, I don't know if some people are just easier to convince of all kinds of things. Like, There's all kinds of conspiracy theories, and some people are just easier to convince of a conspiracy theory than others. And similarly, I would imagine that some people are just easier convinced that they're talking to a human than others. And I'm just not so sure how to determine who's the right kind of interrogator. Anyway, I'm going to leave that a little bit open ended, but I think it's an important objection to this Turing test. Also, it's a bit of a moving target because the more we study, the more we become intelligent about what's going on with the computer, perhaps the more we move the bar of what we expect. Um, like maybe when large language models like first come on the scene, maybe we're really impressed and we start to think that this thing's um, could pass the Turing test or something, or maybe some people are convinced that they're talking to a human. But then the longer that we interact with it, the more that we probe it, maybe we become more keen on like what is not quite right about it. So it's not clear like how much time you should have to interact with the machine in order for you to decide that it's human or not. It is an interesting question though to like see if you could do the opposite, like have a human actually talking with a human and try to get it to and try to convince the interrogator that you're a machine. That's like a reverse Turing test that I think would also be interesting from like a psychological point of view, not necessarily from a philosophy of mind point of view. But anyway, I'll just leave that in passing. At this point in the paper, though, Turing goes into a series of what he calls objections to his point of view. And I will say at the very top that not all these objections are very good. Like it's not so clear to me that that Turing's picked out like the best objections to his view. By the way, before I get to there, I forgot to mention that he goes into his whole part of the paper I'm not really going to talk about where he defines like what are the machines that are allowed. He talks about digital computers, talks about the universality of digital computers. He talks about discrete state machines as like a way of idealizing and being able to work with these things. And he talks about how digital computers can mimic any discrete state machine, which is like the idealized version. And this part of the paper brings up another famous result of Turing, which comes into his paper called On Computable Numbers with an application to the Einstein's problem. I can't say that. Um, which was published in the Proceedings of the London Mathematical Society in 1936, where he defines Turing machines, which is like this very, very simplified, uh, theoretical model of what a computer does. And he shows that the halting problem is like this undecidable problem that no Turing machine, you couldn't program a Turing machine to be able to decide whether a program is going to halt or not. And what's interesting about that to me is that there's something called the Church-Turing thesis, which says that if a problem that can be presented to a Turing machine is not solvable by a Turing machine, it is also not solvable by any machine following natural law. So the idea here is that a Turing machine, if you look up YouTube videos about Turing machines, you'll find this very, very simplified thing where there's like zero, ones, and twos, and a tape moves back and forth, and you have some memory. And it just feels like a super simplified version of a computer. And you might say, oh, okay, cool. You mathematicians, computer science, you love to just kind of do this abstract nonsense, but this is not really what a computer is doing. And what the Church Turing thesis says is that no, that's not the case. We designed a Turing machine during Turing designed it to be super simple on purpose so that he could prove things about it. But it turns out that you can show in some essential way when it comes to like theoretical computability concerns that basically any machine, any computer that we've um, created is equivalent to a Turing machine in the sense of deciding whether a question is decidable or not. Um, and so that's pretty interesting. So it's even though a Turing machine is like this idealized and very simplified version of a computer, it's super cumbersome. You'd never actually program a computer or build a computer that way. Nonetheless, for theoretical concerns of computability, it's equivalent that if it's computable on a Turing machine, then it'll be computable on a regular computer and vice versa. If it's not computable on a Turing machine, then it's not computable on a regular machine, right? So we're not talking about the amount of time it's going to take to compute these things. We're just talking about whether it's possible to compute them. Okay, so that whole part of the paper I'm not going to say much about except for what I just said. Um, and now I want to go into the series of objections that Turing considers to his view. And the first one, they all have a heading to them. The first one he calls the theological objection, right? So the objection goes something like this in a simplified form. Thinking is a function of man's immortal soul. God has given an immortal soul to every man and woman, but not to any other animal or its machines. Hence, no animal or machine can think. Of course, he's giving a somewhat simplified version of this argument, perhaps. But this goes back, I think, to some degree to like dualism, where or even Plato's view of the soul, that like the soul is separate from the body, right? Yeah, the brain is part of your body, but the soul or your mind is somehow this other thing that's eternal, perhaps, or lives on after you die. And the brain, or sorry, the mind and the soul, which I'm using sort of synonymously here, have to interact with the brain, have to interact with the body in some way. So you have to explain that interaction, but they're separate. And so if you have this sort of dualist position, which is common in Christianity and other religions, but also several different philosophies, including Plato's and Descartes, famously, um, then you could argue that like what makes machines don't have souls, and so that's why they're not thinking, right? By the way, this is going to bring up this issue of it's not just about thinking, there's consciousness. Anytime you try to distinguish whether something's thinking or not, you're going to also wind up bringing up the question of consciousness. So that'll come up in a little bit as well. And he doesn't really engage with the dualist part here, the dualist philosophy per se. But he does point out that it appears to me that the argument quoted above implies a serious restriction on the omnipotence of the Almighty. I think his point here is that um, if you believe in a God, which I think he's trying to be agnostic towards right here in this part of the argument, he's just saying, though, if you do believe in a God, is it so hard to believe that a God could put a soul in a machine or a God could put a soul in an animal? It's not clear to me that animals don't have souls. If I have a soul, it's not clear to me that anyone has a soul. But if I have a soul, then it seems like it's could be possible that an animal has a soul, and um, it also seems plausible that a machine could be made to have a soul. I guess the point of this objection, though, if I want to take the theological argument somewhat seriously, is that they're arguing that although God could maybe give a machine a soul, he hasn't. It's like not part of his plan or something. Um, and I don't know. I don't know that Turing really gives a strong rebuttal to this argument. Um, and I'm not so sure that I take this argument all that seriously. Uh, but it is the first one that he brings up. And I guess, this brings up some other questions about philosophy of religion here. But I guess his point is that if you could imagine God giving a soul to a machine, then perhaps it's that means that it's theoretically possible that we could build a machine that had a soul. I'm not sure that that follows or not. But anyway, I don't want to spend too much more time on that particular part of the part of the paper. Um, the second one he calls the heads in the sand objection. And what's interesting about these objections is not all of them I think Turing thinks is like actually good arguments. Sometimes I think he's just trying to survey the way that humans react to this question that he's thinking about in this paper. And some of these arguments I think he actually thinks are like legitimate arguments that need to be addressed, and some of them I think are just like um, acknowledging our own sociology or psychology of how we react to certain questions. And the second one I think is definitely of that style. Um, he says that the heads in the sand objection is roughly the idea that the consequences of machines thinking would be too dreadful. Let us hope and believe that they cannot do this, right? Cannot do so. And he says that we like to believe that man is in some subtle way superior to the rest of creation. It is best if he can be shown to be necessarily superior. So then there is no danger of him losing his commanding position. The popularity of the theological argument is clearly connected with this feeling. It is likely to be quite strong in intellectual people, since they value the power of thinking more highly than others, and are more inclined to base their belief in the superiority of man on this power. So I think his point is just that, like, although we might, as human beings, feel uncomfortable and even feel like our ego is being attacked when we think about the fact that machines can think or something like that, that's no good basis for believing that machines can't think or for ignoring the problem. Just because it's unnatural for us or feels scary to us is no good reason not to think about it. Is no good reason to think that it can't happen, right? All right, so let's move on from that objection as well, because I don't think it's a very serious objection, but I do think it is worth sort of bringing up because it is a very common reaction. Actually, this reaction reminds me also of how humans tend to react to the idea of not having free will. When you try to talk to someone about the potential that we do not have free will, oftentimes people get angry or frustrated, and it's not because I think the argument that you're giving is illogical or something like that. I think it's somehow who we are psychologically does not like to be presented with the possibility that that we don't have free will. In fact, this reminds me of a Ted Chiang short story in his collection of short stories called Exhalation, where he has this machine that is designed in such a way that it can show humans that they don't have free will. We don't need to get into the specifics of how it works, but it's just some machine that when a human interacts with it, they have the realization that they don't have free will. And what's interesting about the short story is that these humans then sort of like short circuit, like they have a hard time functioning with this realization that they don't have free will. And it points to the our psychology more than it does like an argument for whether or not machines can think, right? Okay. Now, the third objection I think is a little bit more substantial, though also I think is going to be um, he's going to show is not good enough here. But this one is called the mathematical objection, and basically it goes something like this. Gödel's incompleteness theorem says that like any formal system cannot decide the truth or falsity of every statement that that formal system can make. There's also the halting problem by Turing, which shows that there are these problems that cannot be decided by a computer machine. And the argument goes something like this that, machines are basically some kind of formal system. And so they're subject to Gödel's incompleteness theorem, they're subject to the halting problem, and various other results in mathematical logic and computability theory and things like that, which limit what formal systems can do. And then the argument goes something like saying that human minds are not a formal system and are not limited in the same way, and hence that's why we're different than machines, right? Um, and the problem is that it's not clear why we should believe that humans are not just some kind of complicated formal system of some sort, right? Like it's not clear why we shouldn't at least we shouldn't think it's possible that we are somehow in maybe a very complicated way reducible to some kind of formal system that's subject to the same limitations as Turing machines or something like that. And I think it's interesting to think about whether or not humans are subject to those limitations or not. Um, I'm not going to go too much into that here, but I think for Turing, all he has to point out is that it's certainly not obvious that we are different than a Turing machine or than a formal system. So as long as that's the case, um, this argument doesn't really work. So unless you can prove to me or give me some reason to believe that humans are not just some kind of Turing machine, or at least equivalent to a Turing machine in some way, then he can keep going on with his with his argument. Now, I think for this part of if you really want to argue that humans are different, then probably your metaphysics is going to involve maybe some kind of dualism, like that there is a soul that's different from the body, or or maybe some kind of panpsychism or something. There's going to involve some kind of metaphysical claim that's other than like strict determinism or uh or materialism, where usually materialism, that like everything can just be boiled down to like the results of physical processes. Usually that's going to involve some kind of agreement that we're just some kind of like result of a formal system of some type, or some kind of, or equivalent to a Turing machine in some way, even though the brain might be extremely complex and we cannot create such a thing yet. It usually involves some kind of claim that we can we should expect eventually to be able to create something like a brain, or at least it's theoretically possible that one could be created, because it is just a um, product of physical processes, right? So if you want to deny that and you want to say that the brain is not equivalent to like these limitations on formal systems, then you're going to need some kind of metaphysics that makes clear why that's the case, which sort of makes clear why um, human brains or minds are not just equivalent to a Turing machine, right? So anyway, he's not going to go any more into that in this paper, so I should stop there. Um, the next one is called the argument from consciousness, and here the issue or the argument, in very simple forms, is that computers are not conscious, and that's what makes them different, right? Um, And here, I'll read a quote from the paper. According to the most extreme form of this view, the only way by which one could be sure that a machine thinks is to be the machine and to feel oneself thinking. One could then describe these feelings to the world, but of course, no one would be justified in taking any notice. Likewise, according to this view, the only way to know that a man thinks is to be that particular man. It is, in fact, the solipsist point of view. So he's saying that this objection says that the only way we can know whether machines think is to know that they're conscious. And we couldn't possibly know that a machine's conscious because, well, we'd have to like be able to feel its conscious thoughts or something, right? And by the way, again, it's because Turing thinks that what it means to think is simply a function of your behavior. The person that's arguing against that in the form of consciousness is saying, no, 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 it's not just your behavior. You also have to be conscious. That's what makes you a thinking thing, right? Or a human being or something. Um, and so, we need to know whether the computer is conscious or not to know whether it's thinking, and we can't possibly know whether or not it's conscious, right? Does it have an experience of what it's like to be itself? Is usually uh, which is comes from Nagel's "What It's Like to Be a Bat" analogy of what we're talking about when we talk about consciousness. Well, first of all, it's interesting because along with the question of whether computers can think, there's also this question of whether computers could become conscious or not, right? Which is not an easy question to answer, and this is related to what's called the hard problem of consciousness, which was made famous by David Chalmers, which says something like you have to explain why human beings are conscious, like, because you can imagine that we could just be these zombies that do exactly what I do every single day, but yet does not have a conscious experience of doing that, like doesn't have any sense of what it is like to be me while doing it. And that's why we call it a philosophical zombie, because it does everything that I do, it just doesn't have an experience of doing it. And so David Chalmers is famous for pointing out this, or making this question really big in the philosophy of mind and philosophy of consciousness. And he says that we need to give some explanation for why it is the case that we're not philosophical zombies. Now, that's a slightly different question, because again, the question of consciousness is very much related to what it means to think, but I think are separate questions. Um, but what Turing points out, because again, Turing's point of view here is a little bit more practical. He's trying to give you a test. He's trying to give you some kind of test to see whether someone's thinking or not. And so he attacks this consciousness argument from a very like practical testing point of view and says, well, yeah, sure. I don't know whether a machine is conscious, but he also points out that I don't know that other people are conscious, right? In the strict philosophical sense, I have no idea that like my friends are conscious, right? I project that belief onto them because they seem to interact the way that I do. They seem to talk about themselves as if they are conscious, just like I do. But I don't know that they have a conscious experience of themselves. For all I know, everyone else in the world is a philosophical zombie except for me. And maybe I'm the only one that has conscious experience. I know I have conscious experience because I actually experience it. We can go into lots of more philosophical issues there, but I think at some base level, I have at least some sense of having consciousness. Um, but I really have no reason to believe with the strictest level of certainty that anyone else has consciousness. This is called the solipsist point of view that perhaps I'm the only, conscious mind in the world. I believe that there's no way to escape solipsism without just making a reasonable assumption and saying, okay, I can't prove to you that other people are conscious, but I'm going to make the assumption that they are and reason from there because how else could I live? And anyway, his point is just that you can't even decide whether other people are conscious, yet you're going to assume that they are. And so just because you can't decide whether a computer is conscious doesn't seem to have as much bearing on this question of whether they can think. Um, and so he kind of points out that whether or not machines or other humans are conscious is sort of a separate question from whether they machines can think or not. Um, so he deals with that way. I think he's got a good point here. Though I think there's probably other ways you could try to make an argument like this. And when we get to so I'm also going to read other papers on whether computers can think and artificial intelligence and the mind and consciousness and things like that. I think other philosophers after him have made more sophisticated arguments related to this. Um, but it's interesting because he brings up this problem of consciousness here because he mentions later that he thinks a lot of the other arguments he's about to go into basically a lot of times are the argument from consciousness in disguise. Okay, the next argument he calls the arguments from various disabilities. And he roughly states that the argument goes something like this: I grant that you can make machines do all the things you have mentioned, but you will never be able to make them do X. And X represents, he gives a bunch of examples. You'll never be able to make them be kind, resourceful, beautiful, friendly, have initiative, have a sense of humor, tell right from wrong, make mistakes, fall in love, enjoy strawberries, use words properly. That one, I think, has been debunked with large language models for the most part. Be subject of its own thought, have as much diversity of behavior as man does something. And, you know, he points out that, well, for one, just because you can't create a machine to do all those things, I'm not so sure that that means they can't think. I mean, don't get me wrong. I think a lot of these things that I just mentioned in this list that Turing mentions are what makes humans beautiful and unique. And I think there's like a version of humanism there where we celebrate these things about ourselves, but somehow that feels tangential to the question of whether machines can think. Like these are two different questions, it feels like. And it brings up this thorny problem that, and I think this is part of why Turing thinks this question's a little bit too vague and doesn't make sense, is that there's so many different ways you could try to define what it means to think. And that's part of the issue here. Like, does falling in love have to do with thinking? Like, that doesn't seem like the same thing. Falling in love is a very beautiful part of being a human being, but I'm not so sure that that's what it means to think. Um, Also, like maybe machines could eventually fall in love. Like, I don't know. It's hard to really argue one way or the other there. And yeah, I don't know about that. And, maybe machines are thinking, but they're just not doing it the way we do. Right. And that's where we have to kind of sharpen up. And I think Turing is right that this question is like too open ended and too vague. We have to sharpen up what it is that we're looking for here, what it is we're trying to distinguish. And I will give Turing at least this much. He at least gives us a test which um, tries to give a very sharp distinction between what it means to think and not, right? So he does at least that much. And he talks about how he thinks a lot of these arguments that, oh, machines can do, I'll grant you machines can do this, but they'll never be able to do that, come from a misapplied form of the law of induction, meaning that they've seen machines do certain things their whole lives, and then they just induct and assume that, oh, that's what machines can do, and they'll never be able to do anything else. And he's just saying that that kind of induction is misapplied. That, first of all, in 1950, they hadn't seen really anything much of a machine at that point, and even in 2025, oftentimes we try to do the same thing. We try to project to the future and say, oh, I'm sure machines will be able to do this. They can solve all these tests and they can do all this different kind of work, but they'll never be able to, you know, fill in the blank, create a really beautiful piece of art, or, create a really moving movie or something, or, you know, I don't know. And the problem is that we just don't know. Like, we just don't know, and we can't look to what computers have been able to do in the past and use that to project forward to what they're going to be able to do in the future. I mean, just think about what computers people had in 1950 versus what we have now. They probably would have been super surprised by the kind of computers and the kind of things that computers can do now. Um, and he brings up, one issue here I think also is like, I think we would say that like chimps or monkeys and these different species which are somewhat related or close to us evolutionarily, that it does seem like they think in some way. And so how do we distinguish between, human thinking versus like these more sophisticated animals who seem to be doing some kind of thinking? Is that thinking different enough? It's just supposed to be an analogy to make us realize that, um, maybe computers are going to think in a very different way, but yet still they're going to be doing something that we should be calling intelligence or thinking. I don't know. He also talks about how people argue that machines are perfect, they don't make mistakes, and that's a issue. But he talks about in the Turing test, of course, that machines are going to try to imitate humans, and so if they're sophisticated enough, they'll just make mistakes intentionally that they think are um, the kind of mistakes that humans make in order to seem like a human. And then at some point, he talks about how people will argue, oh, well, computers can never be the subject of their own thought process, and that's what limits them. And this is where I think he's talking about artificial general intelligence. And he again points out that we don't know that. Like, you can say that confidently, and you might be scared of the fact that computers might be able to eventually be the subject of their own thought process, but you can't say with 100% certainty that that's not possible. So it's not really an argument. It's more of a projection of your feelings, it goes back to, the heads in the sand objection that he brought up earlier, perhaps. So, and he also talks about how this oftentimes is a disguised argument from consciousness, that we view some limitation as somehow a limitation in the computer's lack of consciousness. Um, but really, we just don't know what's possible here. Okay, so moving on to the next objection. This is called the Lady Lovelace's objection. This is named after Ada Lovelace. She was a mathematician and writer, oftentimes called the first computer programmer, because she programmed a machine that could do calculations and things. Um, with Charles Babbage, that inventor of the analytic engine. And so she's oftentimes called the first computer programmer. She lived from 1815 to 1852. And so she's way before even, 100, she dies 100 years before this, roughly 100 years before this paper is published. And so, um, and her objection is that machines can only do what we tell it to do. A machine can never really do anything new. And actually, I've found myself making this objection before, when large language models were first coming on the scene. Like, yeah, they can create lots of like low level shows, and lots of us will watch those shows, the kinds of like sitcoms where you just kind of regurgitate good ideas that other people have had and make a new show. And hey, listen, we all watch those shows from time to time. Sometimes we just need some, something to entertain us or whatever. Um, but a machine could never make a truly great show, right? This is like a version of this argument. Um, And I think this comes from experience in the sense that like I've programmed before. I'm not a big programmer, but like I minored in computer programming in college and I've programmed for teaching and things like that. And in traditional programming, the computer's not going to do anything that beyond what you tell it to do. Um, and so, and I think that's where this view comes from. And again, it's sort of like a misapplication of the of induction here from science. And he's sympathetic to Ada Lovelace because she of when she lived. It's not surprising that she would have such a view, but he also points out that we just don't know what computers are going to look like in the future and what they're going to be capable of. And I think we've already seen that, like neural networks and machine learning, and the way that we have been able to, I'm talking about humanity here, we've been able to um, create these large language models is not really in the traditional sense of how we think of programming. And so, a lot of times the behavior of a large language model is somehow the product of some very massive minimization problem. And so, although we program the minimization problem in some deterministic ways, this is very simplified. The minimum that we get under that minimization problem is not necessarily something we can predict, right? So, um, anyway, that's sort of how I see part of this. Um, and a machine can never do anything new. He brings up there's nothing new under the sun, this sort of Song of Solomon quote from the Bible. And he says that better variant of this objection says the machine can never take us by surprise. That's what Alan Turing says here. And this makes me think of the AlphaGo documentary on Netflix, which if you haven't seen, you should check it out. It tells the story of AlphaGo, which is this AI system that went up against the best Go player in the world, Lee Sedol, and won 4 out of 5 games. And during one particular game, um, that was pretty close, if I remember correctly, like it was a pretty competitive game, I think. There's some point in the game where the AI system makes a move that like no human would make, but the people can recognize it as like a beautiful move, that like there was some sophistication to this move, and people were genuinely surprised. So, sort of according to Turing's test, in some way, the fact that we were surprised indicates some kind of intelligent behavior. Again, it's behavior for Turing's test that tells you about intelligence or tells you about thinking. So, the fact that the AlphaGo system did something surprising is a behavior which is like human behavior and is the kind of thing that would make you think that I was a human, right? And so I think this idea that you can't be surprised by a machine is just not correct. And I think that's what Turing is trying to point out here. And he's pointing out that it made sense for Ada Lovelace to have this opinion back when she was around, but and maybe in 1950 this is a very natural opinion, but certainly in 2025, I think we've been surprised enough times now to know that we're probably going to continue to be surprised, especially over the next, 10 to or 5 to 10 to 20 years or whatever. I think we're going to be continually surprised at what machines can do. And we're going to have to keep going back and asking ourselves, what does this mean for whether or not machines can think or not? Okay, number 7 is called argument from continuity in the nervous system. I have very little to say about this part. It just says something like the nervous system or the brain is not a discrete state machine. But he points out that basically the imitation game is set up so that the difference between how a brain works and how a discrete state machine works is not something the interrogator in this test can take advantage of. And so it's just not a good objection in his mind, right? Like he's just trying to say that he set up the test in such a way that the interrogator can't see the machine or the human being. So it has no way of looking at the architecture involved and making a decision based on that. The interrogator goes solely based on behavior, right? This is his whole point. And again, later people have argued against this point of view, but I think This is very much Turing's point of view in this paper. Okay, now we go to argument 8, the argument from informality of behavior. And he says, it is not possible to produce a set of rules purporting to describe what a man should do in every conceivable set of circumstances. And he gives a version of this argument where he says, if each man had a definite set of rules of conduct by which he regulated his life, he would be no better than a machine. But there are no such rules, so men cannot be machines. And he points out here a distinction between what he calls rules of conduct and rules of behavior, laws of behavior. And he says that this is where there's like an equivocation, or he says undistributed middle in this argument, which is a type of fallacy. I'll try to explain the fallacy slightly differently. I think his point is just that, yes, it's true that we've never written down a set of rules of by which I observe people following. And also, if I look at people, it doesn't seem like I like I look to a certain set of rules or some kind of program consciously and say, "Oh, the program tells me to do this," and then I do that, right? Sure, we will grant you that that's not how humans seem to work. We don't literally respond to a program in our consciousness, right? We can't like literally put down we doesn't seem like we literally put down a set of rules and then follow those at how we live our lives. But that's not really the point. Like whether I'm conscious of the rules I follow or not, it doesn't mean that there aren't these sort of what he calls laws of behavior, which are somehow, again, this gets back to materialism or strict determinism or something like that, where if there are these like base laws, maybe just like what's in our DNA, right? That decide what I do, and maybe in a super complex way that we'll never be able to map out. But the very fact that we seem to think that there are like DNA is this sort of like programming, if you will, that I'm not conscious of, but is determining in some way what I do. That alone means that this argument doesn't work because maybe I do have like just a very sophisticated set of rules that is determining all my actions and behavior. It's just I'm not conscious of them, and they're just really complicated, right? So this argument does not work for Turing, and I do agree with him. If you want to make this argument, then you have to somehow give me, I suspect, some kind of metaphysical argument where you explain why I cannot just be reduced down to a set of laws of behavior. Right? You have to somehow tell me why this materialist position that everything can be boiled down to physical processes in the physical world. Um, you have to break that somehow metaphysically and tell me what the consequences of that to try to make this argument correctly. But since I certainly don't think there's like a completely knockdown way of doing that. You might be able to persuade me, but I don't think there's a completely knockdown way of doing that. And so Turing argues that just because of that, he says basically just because we cannot figure out the laws of behavior does not mean that there are not laws of behavior that govern human beings. And so, um, but also the Turing test is not necessarily about determining those laws of behavior at all, right? The Turing test is rather about observing behavior and deciding whether it's human or not, right? Or whether a mind can imitate a human or not. Okay, now we come to the last argument, and this is really bizarre, actually. I was quite surprised by this. So, this argument is called the argument from extrasensory perception. Now, you ask, what's extrasensory perception? Isn't that ESP? Why is he talking about ESP here, right? What the heck's going on here? Um, I'm surprised at how serious Alan Turing seems to take things like telepathy, clairvoyance, precognition, psychokinesis. Um, these disturbing phenomena seem to deny all our usual scientific ideas, how we should like to discredit them. Unfortunately, the statistical evidence, at least for telepathy, is overwhelming. I don't know what evidence he's talking about. I don't know what he's talking about here. Um, I have no idea. I'm quite perplexed by this. I mean, Turing seems like the kind of person that doesn't want to entertain like really bizarre mystical ideas, but yet in this last objection, he's willing to entertain telepathy. Like, does this come from some kind of like projection of what the bizarre stuff that happens in quantum mechanics at like the very minute, level, and then somehow maybe that's where telepathy comes from? I don't know. But basically, the way he gets through this part of the argument, he says, well, in the Turing test, we could just design it so that there's a telepathy proof room. And as long as there's a telepathy proof room, then this telepathy thing won't like mess with the experiment. This is so weird to me though. Even the solution is weird to me because it's like, first of all, I don't think telepathy happens. If I started seeing experiments that showed telepathy enough times, again, don't get me wrong, a good scientist has to eventually be convinced that this thing is happening and try to study and understand. But I don't think we've had any experiments that I know of that show telepathy exists. And even if it did exist, though, how do you even know that there could be a telepathy proof room? Like, what does that even mean? Like, I don't know enough about telepathy to know whether I could proof the room. So I'm not even sure how serious he's taking this or not. Like, I don't know. He spends like more paragraphs than you expect on this. Anyway, it's just really surprising. Let's move on though from that argument. I really don't know what to make of that. But in the last part of the paper, we're almost done now. This is the most interesting part of the paper, in my opinion. He acknowledges, okay, I can't just like give negative arguments. I can't just knock down everybody else's argument. At some point, I have to like be positive and try to bolster my own point of view directly, right? So he says something like, or he says, the only real satisfactory support that can be given for the view expressed at the beginning will be that provided by waiting for the end of the century and then doing the experiment described. So he's saying that like he made this prediction back in section 6 that um, eventually computers will advance enough, and he said something like no more than 70% of the time, or maybe 70% of humans will be able to distinguish between a human and a machine. And he admits at this point that like we just have to wait because right now we just don't have the computing capacity to really meaningfully do this test. But he says, okay, but what can we say in the meantime? Like, okay, we can't do the Turing test quite yet, but is there some other things that we can say, right? And again, this gets to like the most interesting part. So he starts to talk about he does this little paragraph talking about the limitations of computers at the current time and how much maybe capacity they'll need to be able to perform the Turing test a certain way and imitate humans. But then he gets into a more interesting part to me, which is um, if we want to try to imitate the adult human mind, there's a few things we might have to do, right? So there's kind of three components. There's the initial state of the mind, say at birth. There's the education to which it's been subjected. And then there's other experience not to be described as education to which it has been subjected. And so what he says is instead of trying to just produce a program to simulate an adult mind, like why don't we just try to do exactly what humans do, which is to like create some kind of child and then educate it somehow, just like we educate our own kids. And perhaps if we create a good child program, whatever that means, and educate it sort of like we do our kids, perhaps that's the right way to create machines that can think similar to humans or in a way that will pass the Turing test. Now, this also reminds me of another short story by Ted Chiang that's also in Exhalation, where he talks about digients, which are these machines that do exactly that. They start off with some like initial state of a computer, but they're like very low sophistication, and you have to like teach it, and it evolves over time, and it learns over time from its owner some things, and eventually becomes much more sophisticated. And it's interesting because I saw Ted Chiang at a New Yorker magazine festival with Daniel Dennett about a year and a half ago. This was before Daniel Dennett died, of course. And they were talking about artificial intelligence. And at one point, Ted Chiang mentions this last part of the paper, the very paper we're talking about now, and how he finds it to be very interesting and how he thinks that, we should try this approach of like actually trying to teach a computer, like trying to make like a baby computer in some sense, just something very simple, and then like teach it over time. And maybe that will be the best way to create a sophisticated computer that can think in artificial intelligence. What's interesting is that, oftentimes when you hear about artificial intelligence nowadays, well, you hear things like, neural networks and machine learning, right? And the point is that although it may not be learning exactly the way that Turing's getting at here, it is we have sort of taken this idea to some degree, which is this idea that we need to create if we're going to do artificial intelligence, then this artificial intelligence has to be able to um, learn in some way, right? It needs to be able to like update in some way, and this is how AlphaGo was able to get good at Go, by the way. They give it some like very sort of starting point, but then they have it train on all kinds of different Go games. And every time it plays a player, it learns something. It can play itself and learn something as well. So there is already this idea of learning involved in the way that we program artificial intelligences today. He talks about how like evolution is slow, right? That we've gotten to the point where we are via evolution, but evolution is super slow. It takes billions of years to like make these random um, differences and then select some of them uh, by selective pressures and so on and so forth. It takes a very long time. But in our case, we can do this sort of more intelligently, more quickly. We can notice a mistake and then change it right away, or try lots of different things and update right away. And so he just points out that evolution is slow, but we don't have to be as slow as that. He talks a little bit about punishments and rewards and how can we need some kind of reward system and penalties to be able to teach these machines to think. And I'll just read some quotes here at the end. An important feature of a learning machine is that its teacher will often be very largely ignorant of quite what is going on inside, although he may still be able to some extent to predict his pupil's behavior. This is interesting because this is still true. This has been true for a while of neural networks and machine learning today, that we don't really know exactly what's happening in the system. Again, these things in a very simplified way are super, super large minimization problems. And we do program the minimization problem, we program the algorithms to find the minimum, but we oftentimes don't know exactly what's going on inside the system of weights and things in the neural network that's determining the behavior. Like we don't have a good way of completely understanding. It's very much a black box. Like humans programmed it, but the essential feature of what's going on to create the output is not clear. And this plays right into Turing's view, though, because his view is that we should just study the behavior, and it doesn't matter what's going on in the black box. What matters is the behavior on the other end and whether it looks like an intelligent behavior or not. The question is whether we can decide whether behavior is intelligent or not. And for him, it has to do whether you can convince a human being that they're talking to a human being. Um, and I'll read this last quote. The view that the machine can only do what we know how to order it to do appears strange in face of this. Most of the programs which we can put into the machine will result in its doing something that we cannot make sense of at all, or which we regard as completely random behavior. Intelligent behavior presumably consists in a departure from the completely disciplined behavior involved in computation, but a rather slight one, which does not give rise to random behavior or to pointless repetitive loops. Another important result of preparing a machine for its part in the imitation game by a process of teaching and learning is that human fallibility is likely to be omitted in a rather natural way, i.e., without special coaching. Processes that are learnt do not produce 100% certainty of result. If they did, they could not be unlearned. And then I'll just go back to this last paragraph and then we'll end there. He says, we may hope that machines will eventually compete with men in all purely intellectual fields. But which are the best ones to start with? Even this is a difficult question. Many people think that a very abstract activity like playing chess would be best. Now, what's interesting is this is 1950. In 1956, there was this machine called the Maniac, which beat a novice at chess. Impressive, but not like the most impressive thing. But it was impressive that it could beat a human being, right? And not the best chess player, but it could beat a human being. But then, more famously, in 1996, IBM's Deep Blue beat Garry Kasparov, which was the reigning chess champion. So that was much more impressive because the computer was able to beat the best human around, and now computers are far superior to humans at chess. It took a lot longer for Go. That's why Go was around, I think, 2014, because Go is a much more complicated game than chess is, as far as like how large the space of moves that you have to search is. So he mentions, these kind of like purely deterministic games as one way of testing whether AI systems can think or not. But then in the second part of this paragraph, it can also be maintained that it is best to provide the machine with the best sense organs that money can buy, and then teach it to understand and speak English. This process could follow the normal teaching of a child. Things would be pointed out and named, etc. Again, I do not know what the right answer is, but I think both approaches should be tried. That's interesting. So this second approach, I think, is somehow we should try to like make machines as human as possible, human-like as possible, like children, and then literally try to raise them like children and see what happens when we do that. I don't think we've tried that actually, and I don't know exactly what it would look like to try that, but it is an interesting idea. It's like again, Ted Chiang goes and runs with this idea in his short story, but it'd be interesting if there's some way to do this very carefully in the real world. I'm not sure if any scientist is taking this seriously or not, or if it just doesn't quite make sense. But certainly, like maybe the point is to like try to mimic evolution in some way, right? Like we seem to evolve. We have these sense organs, we have the consciousness, we have this ability to um, reflect on our own thinking, and um, we are able to learn things, and perhaps we should try to mimic all that stuff about learning and sense organs and things in order to create a machine that can think. I don't know. Turing also seems to not know. He just says we should try both things. We should try everything that we can think of. And then the last sentence of the paper is we can only see a short distance ahead, but we can see plenty there that needs to be done. So he ends it with this very open-ended sentence. Anyway, this paper is from 1950. It's very famous. I enjoyed reading it just because of um, how famous it is. I'm going to actually discuss this with my philosophy discussion group tomorrow. And I'm interested in looking at some objections to the Turing test in other papers that have come out. Uh, in some sense, it feels a little bit, um, a little bit outdated, but it is interesting how clear and how interesting, just interesting to read Turing's paper. So anyway, let me know what you think, like, comment, and subscribe, and I hope to see you at the video discussion.